I know I'm not on mute and I just started recording. So it's pretty good, right? All right. Wait. So I kept this just so we could review it, use it for review. Hey, 5. Now we're talking. There are people online, but it's the ones I can see. So last day we started kind of a big important topic, hypothesis testing, right? Whenever you want to prove something is significantly larger or smaller or better or whatever, you need hypothesis testing. And in general, I tend to break it down into 4 steps, but whatever you find is helpful to kind of walk you through the procedure is good. Okay, I did kind of skip step 0, which is check the conditions. I shouldn't call it step 0, but it's a lot of work and a lot of memorization for not a lot of reward. And so that's why I'm kind of skipping it for now, and then we'll fill in the blanks as we go. Okay? But for a hypothesis test, and I said, okay, a hypothesis testing question is generally out of 7 marks. Okay? And so for 2 marks, step 1, you're going to state the hypotheses. Tell me how you interpreted this question. And we talked about, okay, well, we have a null hypothesis, and it has to be about a parameter. And where we're starting is with 1 sample proportion. And so that parameter has to be the population proportion, right? How does this population proportion compare to some number? Okay? And so this is going to be a proportion that you grab from the question, that P naught. Okay, so H naught or P naught is usually how we name them. And then our alternative hypothesis is that P, so we have to talk about the same thing here and the same thing here, right? And so then the alternative is that it's not equal to this number, right? We don't commit to what it could be, right? That brings us back to a confidence interval, but we do say, okay, well, there's evidence against it being P, and so then I conclude that it's not P naught, okay? Often, the alternative hypothesis is the thing that we're trying to prove. And not always, but often. Okay? And we do all our testing assuming that the null hypothesis is true until we have enough evidence against it, right? So we assume that P is equal to P naught until we find, oh, okay, that's actually pretty unlikely, right? And that brings us way down to the P value later. So many P's, right? But we do everything assuming that the null hypothesis is true until we find pretty unlikely, okay? And then we reject H naught in favor of HA. Right? And this is all from last day, so I am going fast. Okay? This is from your formula sheet. All right, so once you've decided what type of question you have, that's a huge skill to have, is to read a bunch of questions and figure out what type of question you have. I do kind of a fire drill on test 2, where do you guys know what a mad minute is? It's like in grade school, you had a 1 minute to do 100 math questions. Just a mad minute. So I do like a mad minute, but for hypothesis testing, where you just have to read, not that stressful, but you have to read the question and just tell me what type of question it is, right? And so that you can kind of drill through these and figure out, because that's a huge skill, right? Especially on the final exam, where they're all in a jumble, right? And you have to figure out, okay, what type of question is this? Because that really zeroes you in on the formula sheet. And then you just follow all the steps, right? Shouldn't say just. But on your formula sheet, once you've decided you have a 1 sample proportion type of question, then I tell you, okay, if you're doing a hypothesis test, this is your null hypothesis. It is your job to figure out what P naught is. P naught is a placeholder for the number that you want to compare your sample proportion to, and it's going to be in the question. Okay? Which brings us to step 2. Step 2 in this case is calculate a test statistic, or in any case, is calculate a test statistic. I call it do the test. I think it's catchier, do the do. But the test statistic is always given on your formula sheet, right? And so step 1 and step 2 are kind of halfway given to you on the formula sheet, right? And then from there, once you have your Z, you know how to find areas under the curve with a Z, right? Because that Z behaves the same way you always, all the other Zs that we've seen. Now, in general, a test statistic is going to have the form of a point estimate, so your best guess from your sample, minus the hypothesized value, divided by the standard error of the point estimate, okay? Which means that P hat is your point estimate, right? That's your best guess at what your population proportion P is. How far is it from P naught, your hypothesized value for P? Hey, I think P is P naught, right? So how far apart are these? Taking into account the spread, the standard error, which we're going to calculate as P naught Q naught over N, and then square root it, okay? So this is the standard error of the point estimate for a hypothesis test. Yeah. For a one sample proportion, right, we have it on our formula sheet. I did it twice for some reason, not sure why. Calculating your Z is just 1 mark. It's a work, right? But it's not really the skill that I need you to have, right? The skill that I need you to have is setting up your null and alternative hypotheses. Software doesn't do that for us, right? And so that's kind of the human task. Then we tend to use software to calculate Z and to find the p-value, right? So that's why they're only 1 mark each, because then the meat and potatoes of this thing is that you know what to do with that p-value, right? So once you calculate your Z, then it's time to find your p-value, right? It's hard to communicate. In theory, you could end with the Z if you're able to communicate Z scores to your boss, which you won't be able to. They like probabilities, right? Human minds work well with probabilities. We understand percentages and probabilities, and we can wrap our head around it. Okay. So finding the p-value relies on us knowing the definition of a p-value. And so the p-value is the probability of seeing something as extreme or more extreme than what we saw in our sample, assuming the null hypothesis is true. And so then we said, okay, well, a probability is the area under the curve. And the probability, so the area under the curve as extreme or more extreme, that puts us in the tails, right? So for one sample proportion, specifically, the p-value would be the probability of seeing a p-hat as extreme or more extreme than what we saw in our sample, assuming P is in fact centered on P naught, right? If that probability is high, relatively high, then there's no reason to reject this null hypothesis. If it's small, right, then we start to say, oh, okay, that's kind of unlikely, possible, right? Just by random chance alone, it is possible, right? But if the probability is small enough, then we say, okay, we cross this threshold where 0.05 is usually what we use, right? Where we say, okay, the probability of this p-hat happening if P is in fact P naught is very, very small. So that leads me to reject H naught in favor of HA. Now, the p-value, how we find the p-value or which tail depends on the alternative hypothesis. Okay? So if you have a not equal to in your alternative hypothesis, and we didn't really dive very deep into the alternative hypothesis options, but the default is not equal to, but it could be less than or it could be greater than, and that's going to come from the question, right? And that's going to determine which tail, or if you want both tails, that you're interested in. Okay? So we'll talk more about that today, though. So for a not equal to, we call this a two-sided test, right? Your sample proportion happened up here, let's say, but we're just as concerned, right, if it happened down on the other end, just as far away, right? And so then we have this one-sided p-value and this one-sided p-value. If you add them together, or take the one-sided p-value and multiply it by 2, then you get the two-sided p-value. So the two-sided p-value is the one-sided p-value multiplied by 2, right? Or twice. Okay, we did a lot last day. A lot of stuff. For 3 marks, your conclusion. So again, a computer isn't going to, I mean, we're getting there, but generally, right, it's our job to interpret this p-value. And so the conclusion is 3 marks, mostly because there are 3 components, right? And you have to cover all 3 for full marks. So in general, if the p-value is small enough, okay, and then we define that threshold of, okay, well, how small is small enough, less than the alpha level, we have enough evidence to reject H naught in favor of HA. Okay. And so we can think of the p-value as the probability that the null hypothesis is true. There is a technical part of me that says, no, that's not exactly the right thing, but it is a helpful way of thinking about it, right? And so if you think of the p-value as the probability that this is true, then at some point, once you get small enough, right, less than the alpha level, which is usually 0.05, okay, then you start to say, okay, I'm going to reject H naught in favor of HA. Okay. So the alpha level is called the significance level, okay, or the discernibility level is kind of the new terminology that's being introduced, but I have a really hard time with that, so I'll just call it the significance level. Old dog, new tricks type of deal. And so the alpha level is 0.05, okay, or the default alpha level. So if I don't give you an alpha level, you're going to use 0.05. Okay? Some common alpha levels, 0.01, 0.05, 0.1. Right? Those are just kind of some common alpha levels that we use, 1%, 5%, 10%, right? And then we kind of explored which of these makes it the hardest to reject H naught. And we're going to just focus on the one tail, because two tail splits it up and it gets kind of confusing. Okay? So if we're in one tail, then if I set the alpha level to be 0.01 and I color coded it, right, then my Z would need to be bigger than 2.326. And we introduced this new table, the T table. Everyone else is good. Do you have a T table? No. Brand new table. That's awesome. Because the T table gives us these one-sided p-values. And so, and it also matches them up with what Z makes that happen, right? And so one of the ways that we could do hypothesis testing is to say, okay, if my alpha level is 0.05 and I have a one-sided test, then my Z would need to be bigger than 1.645 in order to reject H naught. because that would make the area in the tail less than 0.05, right? Because the Zs are increasing, but as your Zs are moving out, the area in the tail gets smaller and smaller, so they're linked like that. So an alpha of 0.01 makes it, of these three, makes it the hardest to reject H naught. There are scenarios where it's really expensive to reject H naught. So for example, if we go back to the null hypothesis, a null hypothesis is just everything stays the same. Keep all the buildings as they are, right? The alternative, what if the alternative is tear down all the buildings and build new ones? You don't want to just do that willy-nilly, right? You want to be really, really sure that you actually have to tear down all the buildings before you go ahead and do it. Sometimes it doesn't matter, right? Is there a majority or no? Not really, right? And so sometimes it doesn't matter. Go ahead and put this medicine out to market because few people are dying from it. You want to be really, really sure, right? That's important. And so then you use a lower alpha level, right? You make it harder to reject H naught if it's expensive. And I mean expensive in kind of a broad sense. Okay. When we talked about the conclusion, this is all review, crazy. The conclusion has three parts, and they're 1 mark each. And I did color code them here. The first part of your conclusion is to compare the p-value to the alpha level, right? We said if the p-value is small enough, then we can reject H naught, right? And so how does your p-value compare to the alpha level? So in general, your conclusion might look like this. So option 1, or scenario 1, I should say, is if the p-value is less than the alpha level, right? You've moved far enough into the tail, you're going to reject H naught. Since the p-value of this, right, you always want to show off all the things that you know from all your work earlier, right? And so since the p-value of, let's say, 0.012, right, is less than the alpha level of 0.05, then we can move on to our conclusion in terms of H naught. Remember, we did all our testing assuming the null hypothesis was true. And so our conclusion is only in terms of the null hypothesis, right? We have enough evidence to reject H naught in favor of HA. If the p-value is less than the alpha level, we have enough evidence to reject H naught. And then the conclusion in terms of the question. Now, of course, that depends on the question, but you're just going to rephrase the question as an answer. And we've got an example coming up. So finally, which means blah, 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 blah. Everyone always forgets the conclusion in terms of the question. Arguably, the most important part of the conclusion is answering the question. But at this point, you've done a ton of work, right? You're tired. You're sick and tired. You don't want to do it anymore. To emphasize, the only change between if the p-value is less than alpha to if the p-value is not less than alpha or greater than alpha, right? I just took this option 1 and I edited it. Option 2, p-value is now greater than alpha, right? The only change that happens is since the p-value of something is not less than the alpha level of 0.05, let's say, then we do not have enough evidence to reject H naught. If you're not rejecting it, then usually we don't talk about HA at all, right? We don't have enough evidence to reject it, and we just leave it there, right? So doesn't mean it's true, right? So that's the important aspect, is that just because we don't have enough evidence to reject H naught, that's just based off of our sample. There's always a chance that we're wrong, and we'll talk about that in a little bit today. Okay? And so I'll make a big deal about this later, but we never accept a hypothesis, right? Because there's always a p-value chance that we're wrong, right? There's always some probability of being wrong. And so that's why these are your only two wordings that you're allowed to use. Okay? And we'll take marks off if you do anything else. I know, but isn't that plagiarism or something else confusing? No. These are your only two options, right? Kind of limited. And then, of course, which means blah, 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 blah. Try this on your own for Wednesday. Here we are. It's Wednesday. Okay. Let's see here. Add a page. Oops. Okay. Wanted to make it bigger. So we've got this Facebook interest categories data that we're working with. And so we've introduced the survey before, and the survey asked the 850 respondents how comfortable they are with Facebook creating a list of categories for them. 41% of the respondents, that tells me it's a sample proportion, right? Said that they are comfortable, I guess. Just they're comfortable with Facebook creating categories for them, but let's ignore that. Do these data provide convincing evidence that the proportion of American Facebook users who are comfortable with Facebook creating a list of interest categories for them is different than 50%? Okay. We're not given a ton of information here, and that's what's really nice about one sample proportion type question is we don't need a lot of information. Okay? And so let's break down what we have. Bless you. We have N of 850. We have a sample size of 850. I only see mention of one sample, right? And so that tells me it's a one sample type of question. Okay? By the end of the course, if you have one sample, you're going to be choosing between one sample proportion or one sample mean. Now, if it's a one sample means question, it'll have to tell you what the standard deviation is, right? And I don't see anything about that, right? And so there's also a clue here. Do these data provide convincing evidence, right? Hypothesis testing is all about providing evidence. And so usually I'll phrase it like, is there evidence that blah, 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 blah. And so here we're talking about the proportion. And so I have one sample of, and I want to analyze the proportion. And so the first thing I'm going to do is say what the type of question is. Okay. We've only seen one type, one sample proportion type of question. And it's not until next week that we'll start to see other types. We lay out all our groundwork with one sample proportion. So once we've decided it's a one sample proportion question, then you can go to your formula sheet, might be nice, and say, oh, you're going to cruise around here and find one sample proportion. And then it's just on that, the last little bit on the first page. Next week, we graduate to the backside of the formula sheet. Big day. right? But deciding what type of question you have tells you where to be in the formula sheet. Right? We could build a confidence interval. There's no mention of making us do a confidence interval, right? But since we want to find evidence, right, we want, so is there evidence, tells me that I'm doing a hypothesis test. You can ignore everything else. In fact, this you can always ignore. It's just there for completeness. Technically it's true, but it's just theoretical, right? And so if it helps to ignore it, that's totally fine. Yeah. Okay. Let's plod through our formula sheet, right? Let your formula sheet guide you. I've set it up so that it's supposed to help you, right? Kind of help you along. We need to figure out, what do I want to compare my sample proportion to? I also need my sample proportion, but once I've decided my P naught is here, my P naught is here, my P naught is here, Q naught is just 1 minus P naught. So again, I already have that. And we already found N. Right? So really all I need here is my P hat and my P naught and my N. Right? We have our N already. Now this 41% of the respondents, that tells me that P hat is a sample proportion. And proportions have to be between 0 and 1. Usually they're communicated as percentages, but you have to convert them to decimals, 0.41. So I found a proportion, a sample proportion of 0.41. What do I want to compare that to? I want to compare it, is it different than 50%? Right? Which tells me P naught is 0.5, right? So that P naught is always going to be the value that you want to compare your P hat to. 0.41 is different than 0.5, right? Really what we're trying to get at is, once we've taken into account kind of variability and we're allowed to move around from different samples, right? Then can we say it's significantly different from 0.5, right? And so that's what we're trying to get at. Okay. Should we do the conditions? Let's assume the conditions are met, and then we can go back to them. They're so annoying. Assume the conditions are met for now. There are conditions, right? In order to be able to assume that it follows a normal distribution and that this is the center and that this is the spread, right? We have to check those conditions. So we have to do it, right? Because otherwise calculating a Z is bad, right? Then we shouldn't be doing that. We should be doing something else. The thing is, the conditions are always going to be met. Or we argue, well, we're going to assume that these conditions are met. And so that's why I'm a little washy on that. But let's get down to business. We saw, is there convincing evidence That's a flag to me. If I want to provide evidence, then it's a hypothesis test. Okay. So this tells me it's a hypothesis testing question. You'll also be able to tell because it'll be out of 7 marks. That's a clue. Okay. So let's call this step 0, which we're skipping. Step 1, state the hypotheses. As I mentioned last week, you don't have to give me the steps. As long as you're doing all the things that are in the steps, I just do it because I'm trying to highlight that we're always doing the same thing over and over and over again, right? And so, so listing the steps is optional. Doing the steps is not optional. You have to do them all. So then I think it just kind of helps to guide you along. Okay. We already decided that this is a 1 sample proportion type of question. So then if I'm doing a hypothesis test, it will be about P, right? I want to hypothesize about the population proportion P. And I also am told that my null hypothesis as a kind of in general is going to be that P is equal to P naught. Right? So we can start here. The null hypothesis is a statement, so I only want to see colons there. H naught is that P is equal to P naught. This we need to alter based off of the question, right? So it's going to be 0.5, the thing we want to compare our sample proportion to. Right? So for us, our null hypothesis is going to be that P is equal to P or 0.5. Okay. Your alternative hypothesis. This is our first one that we're doing with a number, but all the rules stay the same, right? Your alternative hypothesis has to be about how P compares to 0.5, right? So the only change here is the equal sign, right? We've already got the equal sign kind of figured out in the null hypothesis. And so what we're hypothesizing about is, okay, well, if it's not equal to 0.5, then what would I like to be able to say? Okay. Now this is going to come from the question. Okay. We want to know if it's different than 50%, right? And so if there's a difference, I don't care which direction, right? And so then I have if it's different from 0.5, I have a not equal to in my alternative hypothesis. I'll mention it here, but we'll just do this question as cleanly as we can. And then I'll talk about what if this says, is it less than 50%, right? Then you would change this sign to be less than, right? And so a less than sign, you can use 0.41 to prove that it's significantly less than 0.5, right? But can you use 0.41 to prove that it's less than 0.5 or greater than 0.5? No, right? Because it's less than, so it can only be significantly less than, right? And so, but it could say, is it larger than 50%, right? I can already say no, because 41% is less than 50%, so we can't use it to prove that it's greater than. Okay. But those are our three options here for our alternative hypothesis. But let's stick to the proper one for now. Okay. Step one, done. The not equal to tells me that this is a two-sided test. I'm going to highlight that here. Okay. A two-sided test. We don't need that information until way later in step 3 when we have to find the p-value. Okay. Because we need to figure out which tail or both. In this case, we want both tails. Okay. And so we kind of sit on that for a while. But because there's such a huge disconnect, right, we're going to do some math and then we're going to find the p-value. And so there's quite a large disconnect between the alternative hypothesis and whether you want a one or two-sided p-value, right? And so that's why I like to highlight it here. This is optional, but it's a nice kind of way to remind yourself what to do. Step 2, I call it do the test. Technically, it's calculate the test statistic. Boring. Or calculate the test statistic. As we saw, step 1 is on your formula sheet, but also step 2 is on your formula sheet, right? So once you did a lot of work deciding what type of question you had, because now you're just kind of doing whatever the formula sheet tells you to do, right? So from the formula sheet, Z is equal to P hat minus P naught over the square root of P naught Q naught over N. Right? How far is 0.41 from 0.5, taking into account the spread that we would expect? Yeah. Let's see here. Z is, our P hat was 0.41. How far is it from 0.5? Divided by the square root of 0.5 times 0.5. I should say 1 minus 0.5, which is 0.5, divided by 850, right? Our N was 850. No? Let's see if I can get in the habit of using my Desmos calculator here. And will it split it? Okay. So I want to do 0.41 minus I like to do 0.50. I'll wrap that up in brackets and divide by the square root of bracket 0.5 times 0.5 divided by, make sure it's all under the square root. Like that. Wait. Wrap this up. Z is negative because 0.41 is below 0.5. Right? Makes sense. But it also tells us that 0.41 is 5.25-ish standard errors below 0.5. Right? And so that's a lot. That's really a lot. Negative 5.248. I'll do to 3 decimal places. Now, here's the thing. We could use the Z table or the T table, but just so that we can establish kind of the same procedure for most of our hypothesis tests, I'm going to start to use the T table, but I'll show you that you could use the Z table as well. So 3 decimal places for the T table and 2 decimal places for the Z table. Why the discrepancy? Well, we know 2 decimal places for our Z table because our Z table only goes to 2 decimal places, right? Whereas if we go to our T table, right down here, these are all 3 decimal places. So you'd be doing yourself a disservice if you rounded to 2 decimal places, because then you might kind of end up between the wrong 2 values, right? So you just want to match the table is really the rule. Or just keep as many decimal places as you can, and that's fine too. Right? But to use the Z table, you need 2. Okay. This is really far into the tail, right? We know that because we know that roughly 3 standard errors would cover the entire curve, and then it goes to negative infinity and positive infinity, but right, it's very unlikely. So to try to communicate that, right, then we introduce the p-value instead, right? This is hard to talk about. Oh, wow, it's 5 standard errors below the hypothesized value? I can't believe that. That's not really how it would go, right? We need to talk about the p-value, the probability. Okay, so once we have our Z, this Z behaves like all the Zs that we were working with and practicing with before. So step 3 is find the p-value. Remembering that the p-value is if p was in fact 0.5. The p-value tells us the probability of just randomly collecting a sample and finding a sample proportion of 0.41. It's possible, but it's very unlikely, right? And so what happens is we get our p hat equal to 0.41. Okay. We found that it was really, really far away, right? In fact, we found that it was 5.248 standard errors below 0.5. Really far, right? The negative just tells us it's below. We wanted to know if it's different. We're only going to collect 1 sample, right? And so if we want to know, remember that the alternative was that p is not equal to 0.5. Not equal to is just in either direction, right? And so what happens is we replicate this and pretend, okay, well, what if what if something happened 5.248 standard errors above the mean, right? I would be just as concerned, right? Because I want to look at both tails. And so we said this is called did I call it two-sided or two-tailed? Just for, called it two-sided test or two-tailed. I flip-flop between the two. Sometimes I call it a two-tailed, two-sided. Right. Just to say that, okay, we're going to find the p-value. The p-value here, this is the p-value. And I know there are a lot of p's. I know that. There's a lot of probabilities, a lot of proportions, right? And so the area in this tail is the one-sided p-value. And so what we do, if I'm concerned about both sides, which I am, right, then I take my one-sided p-value and I multiply it by 2, right? I just pretend it could have happened in the upper tail as well. So the two-sided p-value is 2 times the one-sided p-value. Right, so we kind of pretend that it could have happened up here as well. To find the p-value, we're going to use the t-table. Because like I said, that'll kind of establish the same method throughout the rest of hypothesis testing. But I'll also show you how to do it. This is a bad example, but later I'll show you how to do it with the z-table as well. Okay, and so you'll have both. Why is this a bad example? If you tried to find the area in the tail for a z of negative 5.248, which is what we're trying to do, you would go to your z-table and you would find, the smallest value I have is negative 3.49. Right? So then all I can really say is that it's less than 0.0002. Right? And then I can multiply that by 2 and say it's less than 0.0004. Fine, I will do it. But first, the t-table. To estimate the p-values, we will use the t-table. I'll grab the part that we need here, copy. Which is just a little shorty version. I'm going to highlight our Z star line, right? We've calculated a Z, and now we're trying to place our Z somewhere on this line. Okay. And then from our alternative hypothesis, we said, okay, I care about both tails, right? And so if we're using the z-table, we could find the area in one of the tails and then multiply it by 2. But if we look at our one-sided p or two-sided p, 0.25 times 2 is 0.5, 0.2 times 2 is 0.4, etc. So they've just multiplied everything by 2. It's not, nothing crazy. Okay. So notice that there are only positive values for Z. Right? That's because Z is symmetric. right? And so knowing what the area in the tail of the upper tail is, we also know what the area in the tail for the lower tail is, right? So there are a couple of missing components here. I like to put end caps here in theory, at least. Yeah? And so if we draw our Z, Z we know is centered on 0, and it's symmetric. So here, 0.674 is the first value, right? I'm just looking at this first value, and it's going to behave as negative 0.674. So what this table tells us is at a Z of 0.674, the area in one of the tails is 0.25. So I draw that like this, 0.25. And if you're interested in both the tails, well, the second tail is also 0.25, or a total of 0.5.
I'm just confused on how we got the 0.674.
Oh, I grabbed it from here. I'm just illustrating with the first one what this and this is doing, or kind of the link here. But I'm also showing you that technically Z is centered on 0 here. Right? So you start at 0. What's the area in one of the tails at 0? It's got to be 0.5, right? Because it's symmetric and the total area is 1. So then you could fill this in with 0.50, and then the two-sided p-value adds another 0.5. So then the two-sided p-value at 0 would be 1. Kind of useless, right? But it's nice to have an end cap. Let's do the same thing on this end. Zs, we know, keep going to what? They keep going to infinity. So let's do, I'll do this stopping point 3.291 has an area in the tail of 0.0005, very, very small. And if we replicate it in the lower tail, negative 3.291, it also has an area in the tail of 0.0005, and together they have a total area of 0.001. Out here at infinity, once you get to infinity, the area past that is 0, right? So the area in the tail here is 0. But it's not until you reach infinity that you get there, that you get an area of 0. Anything past 3.291 up to infinity is, we're just going to be able to say that, okay, well, it's less than, the area in the tail is less than 0.0005, right? But it's greater than 0, right? If you want to have an end cap. Okay? Even multiplying this 0 by 2, we still have an area of 0, because out here at negative infinity, right, we also have 0 area in the tail past that. So what we do is we take the absolute value of the Z that we calculated. the absolute value because we only have positive values on this table, right? And that's okay because by symmetry, it behaves the same, right? So we have negative 5.248. Now, how we're going to set this up always looks like this. The absolute value of Z, and notice how I'm putting it in the center of the page. It's because I'm going to put values around it, right? I need to say, okay, my calculated value for Z is this, and it's between these two values. So here, negative 5.248. This is our calculated Z, right, from step 2. Always put that absolute value, right? You don't want to drop the negative because you did find a negative value, but putting that absolute value on there drops the negative, right? I'll say the absolute value drops the negative. We've seen the absolute value before, but nice to have a reminder. So what we do is we drop the negative and we try to place our Z on this number line. Notice how the Z's are just increasing as I move further and further out into the tails. And I always use less than, right? So it's somewhere between these two values. Right? Just because I don't like working with inequalities, I don't want to have to think about it, right? So here, this is less than, because it makes kind of an L, right? You can read it as less than. So when we try to place 5.248 somewhere on this line, I reach 3.291, end of the road-ish, next stop, infinity, right? So I'm gonna jot that down. So we find that 3.291, and on the upper end, I have infinity. I write the infinity for just kind of consistency. You don't have to write it, but I think it's nice to always do the same thing. So now, my next line, right? If Z is somewhere between 3.291 and infinity, right? Then that's going to translate into a p-value, right? And so my one-sided or my two-sided p-value. Now we need the two-sided p-value because we have a not equal to in our alternative hypothesis. And so I'm going to say the two-sided p-value, or you can say two-sided p, or I'll do p-value. I won't be upset if you put absolute values on here, but you don't have to because probabilities have to be between 0 and 1. And then I match my less than, right? If my Z is between these two values, then those two values are going to give me tail areas, right? Because I'm using less than, I need to, these, as Z is increasing across the page here, the p-values are decreasing across the page, right? And so whatever's to the right, right, is less than whatever's to the left. So you can either read them from right to left, right, and write them down right to left, or you can switcheroo them, or you can play around with your inequality, but it tends to make a mess, right? You don't want to tell me something that's false. So I read them from right to left. So here, my two-sided p-value is somewhere between 0 and 0.001. I'll say read the p-values from right to left. Okay. This is just an approximation. This is good enough for a test, and that's really small. If I tell you, oh, it's somewhere between 0 and 0.001, right, you would say, oh, that's really small, right? In fact, it's less than 0.05. So that's all I really need. Okay, we can use software, and let's see if I have Excel something. I do. I was doing it in a different class. So you can use Excel, and you can use the equals, and you'll have an assignment on it, norm.s.dist, and you can give it a z. We had, no, I can't remember, negative 5.248, oops, 48. And cumulative equals true always for the normal distribution. And you've seen the cumulative command for the binomial and even the Poisson if you tried it, right? And it's just, do you want the probabilities up to and including that point, or just that probability? The problem with the normal distribution is the probability at exactly a point is 0, right? Because it's the area under the curve. And if there's no width, 0 times any height is 0, right? So kind of tricky, but for the normal distribution, you're always going to ask it for cumulative equals true, and it's going to give you just always the area to the left, just like the Z table does. So here we're going to write true. I don't think it needs all caps, but why does it do that? There. I think so. I think it wants all caps, but it'll kind of try to fix it for you. I get something very, very small. On my iPad, it's really hard to tell, but 7.69 times 10 to the negative 8. Whoa. That's the area in one of the tails. Using Excel equals norm.s.dist of negative 5.248 true. We get, what was it? 7.69. Yikes. 7.69 times 10 to the negative 8, which is, okay, here we go. 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7. No, one more. Let's try that. So the 0 or the decimal has to move back 8. 1, 2, 3, 4, 5, 6, 7, 8. I think I did that right. That's the exact area in one of the tails, right? We don't need to be that particular. This is the one-sided, right? This is the exact one-sided p-value. Even if I take that and I say, okay, fine. Now, hey, wasn't it? Oh, I need to be in here. Come on. It doesn't want to do anything. Hey. What a pain. Okay, let's see here. Equals. Why isn't it doing it? I'm just trying to multiply by 2. That's all I'm doing. Okay, let's just do it. Point 1, 2, 3, 4, 5, 6, 7, 8. 1 less. 7, 6, 9 times 2. Therefore, the two-sided p-value is 2 times 0.000. 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6. 1, 5, 3, 8. At the end of the day, who cares? It's really, really small. We were able to understand that it was really small just from this, right? In fact, we had a gut reaction when we saw a z of 5, right? -5. Anything kind of beyond 2 as a rough guide, right? Why 2 as a rough guide? Because if our default alpha level is 0.05 and our default is a two-sided test, then any z bigger than 1.96, I'm going to reject H naught, right? 1.96 is basically 2. So then just as a rough guideline, any z beyond 2, I'm likely going to reject H naught. Okay. But this is all we get, or this is really all you need to show for this step, right? For step 3, find the p-value. This is all you need to show on the test. Then we can use the p-value to draw our conclusion. Step 4 is your conclusion. First part of our conclusion is we say what our p-value is. Now, in this scenario, we don't have an exact p-value, right? But I do have a range. My p-value is between 0 and 0.001. So you can say that, right? And so first thing, we compare our p-value to our alpha level. We weren't told what alpha level to use, so we're going to use 0.05. Okay. So we start like this. Whoops. Since now this is your time to shine. Show off all the things that you know from doing the question, right? You know you had to find a two-sided p-value. You know what it is, right? So tell me all those things. So since our two-sided p-value is between 0 and 0.001, we need to compare that. We can still compare that to 0.05, right? It is less than our alpha level. Than our alpha level of 0.05. If you are claiming that something is less than something, you should support that, right? So it's less than our alpha level of 0.05. That's one mark, right? Kind of how does your p-value compare to your alpha level? And then whatever you tell me, whether it's right or wrong, right? As long as the next part follows what you said, right? Then I'm happy, right? And so even if you're completely stumped on finding your p-value, right? Just say, I'm assuming my p-value is this. And yeah, in theory, you could get a good chunk of marks and not do any of the real work. I know that, but that's okay, right? I'm going to say, oh, my p-value, it has to be reasonable, is somewhere between, I don't know, 0.25 and 0.5, right? Something like that. Make something up. You won't get the p-value marks, but this is only one mark, right? Then if you follow through with that in your conclusion, then I'm happy, right? And so, yeah, in theory, no one's ever done it though. And I mention it every single time I teach this course. In theory, you could just memorize one question. It has to be the correct type of question, right? Still have to memorize a lot of different types, but you could just, this is what I think you're asking in the question. No, it's not. But your conclusion's 3 marks out of 7. That's pretty good. And you could keep all of them. So since our two-sided p-value is between 0 and 0.001, it is less than our alpha level of 0.05, which means we have enough evidence to reject H naught. Right? I'll say, so we have, or maybe I shouldn't use so, which means we have enough evidence to reject H naught. And if you want to leave it there, that's totally fine. But when I say I'm going to reject something, it's always nice to offer an alternative, right, in favor of the alternative hypothesis, in favor of HA. That's another mark. Right? What's your last mark? What does that mean in terms of the question? You have to go way, way back, and you're going to reword the question as an answer. It doesn't have to sound beautiful or anything like that. All right. Copy. Paste. The question was, do these data provide convincing evidence that the proportion of American Facebook users, I think, who are comfortable with Facebook creating a list of interest categories for them is different than 50%? These data provide convincing evidence that the proportion of American Facebook users who are comfortable with Facebook creating a list of interest categories for them is different than 50%, period. Right? So we reword this question as an answer. Therefore, these data provide, and you don't have to put any thought into it. Sometimes the sentence structure is weird. That's okay at this point. You can kind of rework it later, but you're just rewording the question as an answer. So these data provide convincing evidence that the proportion of American Facebook users, I'll add a who there, who are comfortable, whether that makes sense or not, I'm not sure, comfortable with, I'll do FB, Facebook creating a list of interest categories for them is different than 50%, period. That's tedious. That's not hard though, right? That's just annoying, but you just do it. Just rewrite the question as an answer. Right? You don't want to forget that one because that's 1 mark. Right? How's it feel? First hypothesis testing question under our belts. Wow. Lucky you. More to come. They're so long. So you can see how after all this work, you might forget the crucial part of actually stating the conclusion. Yikes. There are a couple of things that we skipped. Okay. Maybe I'll indicate that this is the end of the question here. The end. So what did we gloss over? We glossed over the alternative hypothesis, right? We also glossed over the assumptions. Which one do you want to tackle first? Assumptions, because they're so boring. All right. For 1 sample proportion questions, assumptions. Sometimes we call them assumptions, sometimes we call them conditions. The conditions for inference, right? In order to be able to do what we want to do, we need to check these assumptions. And so this is kind of, I've been calling it step 0. So once you've decided that you have a 1 sample proportion type of question, we've already done a confidence interval, right? We did that last week. And now we did a hypothesis test. And unfortunately, because these questions tend to take a long time, right? We don't get to see a ton of questions in class, but don't worry, I'll give you a bunch of practice. Lucky you. So don't worry, but they take a long time. Okay. But the more you see, you'll pick up patterns and kind of start to recognize some frequently occurring things. Okay. Depending on if we're doing a confidence interval or a hypothesis test, the conditions will be slightly different. The independence conditions are the same. And no, I do want to do it like this. The independence condition, well, we have to be able to assume that all our observations are independent of each other. And so how we do that is a random sample. Can I do a ditto sign even though it's for the one to the side? Does that make sense? Even though it's not below. I wonder what this is called. Hopefully my phone's listening and it'll bring up a reel of some sort. Did you know that the ditto sign, I love those. Is it even called a ditto sign? I don't know. As long as you've sampled randomly, then we can assume that we have independence. The optional one I'll put it here, is that n has to be less than 10% of the population. If you skip that one, that's fine. You will see it in some of the solutions that I have from when I was really, really young and particular about all these things, then I did include it. And then I outgrew it, I guess. You don't have to do it, but you will see it sometimes, right? And the idea being there, you don't want to sample too much of your population because then you're introducing dependent observations. Rarely an issue, right? The overall goal is to have as big a sample as you can. So far, these are behaving the same, a confidence interval and a hypothesis test. I'll bump this over here. Yeah. Random sample and the sample size less than 10% of your population. Then this is where they become slightly different. So there's a normality or a sample size condition. The sample size tells us if we can use the normal distribution, and so I like to think of it as a normality condition. If we're doing a confidence interval, do you remember what we had to check? We had to make sure that we have at least 10 successes and at least 10 failures in our sample. Okay. And so we need at least 10 successes and at least 10 failures in our sample. So in our sample, I'm going to add observed. Whereas if we're doing a hypothesis test, then I need to be able to detect my hypothesized proportion. And so the change here is I need at least 10 expected successes. And I need at least 10 expected failures. So the difference is the observed versus the expected. You would calculate these as n times p hat, or if you have x, that's just going to be x, right? The number of successes has to be greater than or equal to 10. And then for your failures, n times q hat, which is also n minus x if you have x, has to be greater than or equal to 10. The expected successes and the expected failures rely on your null hypothesis, right? And so how we calculate these is we need n times p naught to be greater than or equal to 10. I need to have a sample size large enough to detect this proportion that I'm trying to talk about, right? And so the change being that it has to be about p naught, whereas n times q naught is the expected number of failures. The reminder that I use for myself is I know, I'm a broken record. On your formula sheet. So on your formula sheet, paste this and your confidence interval. Notice that your p hat, q hat is in the square root. Whereas for a hypothesis test, you have p naught, q naught in the square root. Kind of helps guide you, right? Which one to use, right? So at least 10 expected successes. The expectation comes from the null hypothesis, which means we check our conditions first, but it means that we need to read the question and figure out what our P naught is from the question, right? So we kind of need to establish our null hypothesis before we can check the conditions. Right. So we need that null hypothesis, at least kind of in rough form before we can check the conditions. Nice. And that's what you need to check. Depending on the type of question, we've only seen this one so far, right? But also if you're going to do a confidence interval versus a hypothesis test, right? So you need to read the whole question. And again, when I first started teaching, I used to make a question, you had to do your hypothesis test and you had to do your confidence interval. So then you had to check all of these conditions always. Rude. I don't do that anymore. It's a lot of work for you, but also for me. Got lazy. So those are the assumptions or the conditions for a one sample proportion type question, right? Notice that this is always the same. Doesn't matter what you're doing. It's just your normality or sample size condition changes ever so slightly. Yeah.
The X is in the
X is the number of successes. So sometimes it'll be like 68 out of 100 students said this. Then X would be 68. I'll say it here, where X is the number of successes, right? And P hat is X over N.
So you couldn't just do N times P greater than?
You can.
Okay.
I just wanted to show. So sometimes I give you X and N and you have to calculate P hat. And then it's just easier because you already have the X. But if I give you P hat, like in the previous question, right? 850 times 0.41, right? That gives me the number of successes. But there's probably been some rounding. Right? It's going to be greater than 10. What if we had to check the conditions? Step 0, check the conditions for the question we just did. What would that look like? We read on and we understood that we needed to do a hypothesis test, and we have a one sample proportion type of question. And so I need to check, was it a random sample? We can also talk about the 10% condition. And then I need to make sure that I have at least 10 expected successes and at least 10 expected failures, right? And then my conditions will be satisfied. we'll start with the independence condition. I'll scroll way back up, I guess. Should have copied the whole question there. Same survey asked 850 respondents. Now, it doesn't explicitly say in this question here if they were randomly sampled. So what do we have to do? We have to say, I assume these were randomly sampled, right? And so that's why there are the assumptions, and that can be kind of confusing, right? And so so stating your assumptions and paying attention to things that you're assuming is part of the game. Okay? And so I assume that these were randomly sampled respondents, right? 850 is also less than 10%, or it's reasonable to assume that it's less than 10% of all American Facebook users. We assume the sample was randomly selected. You're allowed to say that.
Do you have like a, like, would you get that, did you ever get that wrong if you? Well, I guess.
No, because the problem is, if you tell me that the sample was not randomly selected, then you're telling me that, okay, then you can't assume independence, which means you can't do any of the things on the formula sheet. So you always want to be pushing for, right, no matter what, you want to tell me, I'm allowed to assume that it was random, or at least I can assume that they're independent of each other. Right?
Not random, can't do it, so.
Yeah, just all right. I have had that before. I'm like, really? 7 marks? You thought it was just like nope, sorry, can't do it. It gets 1 mark though, because it's good. You shouldn't do it if you can't assume it. But the and less than 10% condition, I'll give you some common phrasings that we use. Usually we say something like, it is reasonable to assume that 850 is less than 10% of all American Facebook users, right? And so convince your reader it is reasonable to assume 850 is less than 10% of all Facebook users. Sorry, all American Facebook users. Like I said, that one's optional, but we're doing it properly right now. For the normality condition, we had H naught that P was equal to 0.5. I need that 0.5, right? Because I need to make sure that my sample size is big enough to pick up on my hypothesized value, right? 0.5 is going to require the smallest possible sample size, right? But right, because 0.5, I need a sample, I need at least 10 successes, and so I need a sample size of at least 20, right? 20 times 0.5 is 10, great. As we try to detect small proportions, right, something very, very rare, right, intuitively we understand, okay, if I'm trying to pick up on something very rare in a population, I need a big sample size, right? And so that's all that's this condition is checking, right? Is your sample size big enough to pick up on whatever you're trying to put down? So we need at least 10 expected successes which is n times p naught, which is 850 times 0.5, which is 425. That's greater than 10. And I need at least 10 expected failures. N times Q naught, which is 850 times 1 minus 0.5, which is also 425, which is still greater than or equal to 10. The conditions will always check out, right? It's our job to go through and do it. This is a lot of work, right? And usually I just make it 1 mark, and there are little check boxes, and you just have to check the ones that apply. But because it becomes a really long list of options, it's just a kind of a subset of options. And so not all the things that you would have to check would be on there. Right? Kind of confusing, but so it's not really worth the time to memorize it. Do your best, right? You always need a random sample, right? So you can always check that off, right? And then everything else, just kind of do your best, but don't spend a ton of time memorizing this stuff, right? Because it's not worth it. I make it worth 1 mark, but also telling me what type of question is 1 mark. So do that instead, right? Okay. Nice. So then usually we say something like, therefore, the conditions for inference are satisfied. Is that clock, right? And I'm so scared. It's daylight savings this weekend.
Oh my gosh. And then I have an exam on Monday, so
It's not fun. It's not fun. Afternoons are nice. Yeah.
There's more risk of like traffic accidents, heart attacks.
Yeah, it is kind of a dangerous day of the year. Statistically significantly more dangerous than other days of the year. That's been proven. So yeah. What did they have to do? A hypothesis test.
Oh my God. Did you get your hair done?
I did.
Oh, that's good.
Thanks. Thanks. I know. Yeah, it's so funny. I have a coworker. So I used to get my hair done all the time, and then for me, it was just kind of a blip where I didn't for a little while. Turns out it was years because I had a coworker. She's like, I didn't know you colored your hair. I'm like, yeah, of course I colored my hair. What? And then I was like, well, it's only been many years since I have. So. Oh well. I'm back. Okay. So conditions. Boring. How about the alternative hypothesis? I'm trying to decide what I can squeeze in. I think we can do it. So we have 3 options for HA. Depending on the question. So it will depend on the question. So earlier, we had this. I've really drawn on it though. Right. But this different than 50%, right? That's what gave us our not equal to, right? And so what are some other options? Option 1 would be, is it less than 50%? Option 2 would be, is it greater than 50%? Or is it different than 50%? All of them. So in all these cases, our null hypothesis, we're comparing to 0.5. So our null hypothesis is the same for all of these. P is equal to 0.50. H naught is that P is equal to 0.50. And H naught is that P is equal to 0.50. But it's the alternative hypothesis that changes. If we want to prove that our sample proportion is significantly less than 0.5, right, then I want to have an alternative hypothesis that reflects that. So my P is less than 0.50. What if I want to show that it's significantly greater than 0.5? Got it. Genius. And then we already saw, if we want to show that it's different, I don't actually care which direction, right? And so I want the not equal to. So these are my 3 options. We called this a 2-sided test, right? But these, I only care about one extreme, right? And so we call these 1-sided tests. These are 1-sided tests. 1-sided or 1-tailed, doesn't matter. One-tailed or 1-sided tests, and this is a 2-tailed or 2-sided test. How you calculate your Z stays the same, but it's for the p-value. We need to know about the p-value. Okay. And so the p-values is going to look different for each of these scenarios. It's always centered on my null hypothesized value. In fact, can I copy this? Copy pasta. Copy pasta. This one can be smaller because we already did it. So they all look the same. But like we said, if I want to prove that something is significantly less than 0.5, it better actually turn out to be less than 0.5 in my sample, right? I can't use 0.6 to prove that it's less than 0.5. So we're going to find our p-hat somewhere down here, right? Somewhere below, and we're trying to determine if it's significantly less than 0.5, which means that your 1-sided p-value right? The p-value is the probability, it's the area under the curve, of seeing something as extreme or more extreme, assuming the null hypothesis is true. Right? And so this area here is your one-sided p-value. This is a one-sided test, and so that's my p-value. Right? If I'm trying to show that something is significantly greater than 0.5, then I better hope my sample proportion is bigger than 0.5. That's a good place to start. What if it was less than 0.5? Let's just do that as a goofy example. What if you found your p-hat was somewhere down here? The probability of being greater than 0.5 would be all of this area. Garbage. Don't do that. I think there's an assignment question somewhere, buried somewhere, that asks you to use kind of the wrong side, and then the p-value is really, really, really big, right? Which just means that you're not going to reject H0. But usually your proportions are over here somewhere. So then your one-sided p-value is the area in the upper tail. And then for your two-sided p-value, your sample proportion is going to happen in only one of the tails, like we saw, right? But then all we do is we say, okay, well, I would be just as concerned if that happened in the other tail as well, right? And so then I take this area and I multiply it by 2, just like we did earlier. So finding your p-value depends on the alternative hypothesis, but like I was saying, there's such a huge long disconnect between the two that that's hard for people to keep track of, right? But it's there. Fine. I already checked. The clock is right-ish. We can test hypotheses using confidence intervals. There, I said it. We'll pick up here on Friday. If you have any questions, let me know. Otherwise, see you then.